So we're going to continue talking about asymptotes, and let's say we're looking at a function f of x where it's equal to 5 times x minus 3 squared times x plus 5 all over x plus 5 times x minus 9 times x plus 3. Okay, so what we want to think about are essential questions. What we can notice by looking at the function is that the function is already completely factored. So we can actually determine a few things. If we look at the domain of the function, the domain, remember, that is basically all the restrictions of the function. So we want to think about what kind of restrictions does this function have. If we take a look at it, it's a fraction. It's in a fraction form. So what we know about fractions is that the denominator cannot be 0. To look for the values of x that make the denominator 0, we have to actually set the denominator equal to 0. So we can solve for x where x plus 5 times x minus 9 times x plus 3 equals 0. And by using the zero product property rule, we can basically set all of these equal to 0 since they're being multiplied to each other. So we have x plus 5 equals 0, and x minus 9 equals 0, and x plus 3 equals 0. By solving each one for x, we get that x is equal to negative 5, x is equal to 9, and x is equal to negative 3. So that means that if we plug in any of these values in for x, we will have the denominator equal to 0. So this means that for our domain, x can be in all the real numbers except negative 5, 9, and negative 3. If we want to write this in interval notation, then we have to remember that interval notation goes from smallest to greatest. That means that if we think of the number line, we start off from negative infinity, go up to negative 5, stop at negative 5 because it can't reach it, continue at negative 5 because it's just not including that point, then go up to the second biggest number, which is negative 3. At that point, there is another break again, and we are continuing until we get 9, and then after we get 9, we continue from 9 to infinity. We can again think about interval notation as if it was on a number line. So if it was on a number line, it can basically pass through any point except negative 5, negative 3, and 9. So it can include any of these regions. Since the function can get really close to negative 5, negative 3, and 9, these are actually our vertical asymptotes because it will never touch these lines at all. Remember, the function of the form of a vertical line is always of the form x equals something. So x equals negative 5 is one of our vertical asymptotes. We also have x equals 9 and x equals 3, negative 3. If we want to find the horizontal asymptotes, we actually have to think about the degrees of the functions and what the degree is in the numerator and the denominator. So if we actually take a look, we can see that we have an x that is being squared and another x that is being multiplied to it. So we have an x squared times another x. The degree of the numerator is actually x cubed. And that we can get by actually distributing everything. And if we take a look at the denominator has an x being multiplied times another x times another x. So that therefore means that the denominator also has a degree of 3. Since they both have a degree of 3, then that means that we can actually just take the leading coefficients as their asymptote. and the leading coefficient in this case is 5. So our actual asymptote, our horizontal asymptote, would be y equals 5. Again, it has the form y equals because the horizontal asymptote is a horizontal line that the function approaches but never touches. If we wanted to look at what the x-intercepts of the function are, whenever we want to look for the x-intercept, we always want to set y equal to 0. F of x is the same thing as saying y. So in reality, what we're doing is we're setting the function, which is 5 times x minus 3 squared times x plus 5 all over x plus 5 times x minus 9 times x minus 3 equal to 0. We can actually cross multiply from here. So if we rewrite 0 over 1, we can cross multiply, and that actually gets rid of the denominator. So what we're left with is that we have that 5 times x minus 3 squared times x minus 5, x plus 5, is equal to 0. From here, we can just set all of these multiples equal to 0 and solve for x. To get rid of something that's being squared, we have to take the square root of both sides. So the square root cancels out the squared. And then we can just easily solve this from here. So we're left with x minus 3 equals 0. So our x is equal to 3. And on the other hand, we have the x is equal to negative 5. Since our x-intercepts are points, our x-intercepts are 3, 0, and negative 5, 0, because we set y equal to 0. You could also do something similar to find the y-intercepts by just setting x equal to 0 and solving for that. If we want to talk about holes or removable discontinuities or singularities, how last time I mentioned that they were all the same thing, we want to essentially look for if there are repeating terms, if we can simplify the function itself. And since it's already factored, we can actually see that they have the same factor in both the numerator and the denominator because they both have x plus 5, which means that they can actually get canceled out. So because they can get canceled out, so to speak, that means that this is a removable singularity at that point. That point, if you set it equal to 0, is x equal x plus 5. Equal to 0, so you get that x is equal to negative 5. That means that there is a hole or removable discontinuity at x equals negative 5. If you wanted to draw a sketch of the actual graph, you know that there are vertical asymptotes at negative 5, so then it's never going to touch that. If we wanted to draw a sketch of the actual function, we can first label all our horizontal and vertical asymptotes. But what we do know is that one of our vertical asymptotes is x equals negative 5, and what we just found out is that x equals negative 5 is actually a hole. So first, let's draw out our horizontal asymptote. If we wanted to draw a sketch of the actual function, we can sketch out all our vertical and horizontal asymptotes. But as we just saw, x equals negative 5 is actually a removable discontinuity. So we don't have to graph that out initially. We can ignore that for now and graph our other two vertical asymptotes. Our vertical asymptote that we see is x equals 9 and at x equals negative 3. So at those 2 points, at those 2 lines, the graph is never going to touch that vertical line crossing through those points. So it's never going to touch these 2 lines. And there is also a horizontal asymptote at y equals 5. So at y equals 5, the function is never going to cross this line, this horizontal line. Now let's actually graph the function, how that function would look like if it was to be graphed. We can actually go ahead and plot our x-intercepts, but if you guys also take a look, we have that x at negative 5 is a hole. that and a vertical asymptote. What that means is that it's never going to touch that point on the x-axis. It's never going to go through that point, which means that our intercept at -5, 0 is not actually an x-intercept. Our only x-intercept is 3, 0. By plotting that, we actually can plot that into the graph right here. And since it can't go towards any of the other asymptotes, that means that our graph is actually going to be heading downwards. So it's going to be heading down and get really, really close to those asymptotes, but never fully touch it. And the same thing can be said the other way around. So on the top, it's going to get really, really close to those asymptotes up on top, but never officially touch them. And the same thing can be done on the other end. They always have some sort of curvature along those ends. But since at -5 there is a hole at that point, then that means that it's never going to touch this -5. It's never going to touch this point right here, because at that point there is a hole. And this would be a sketch of the function itself. If we wanted to work backwards and find the equation for this graph here on the right hand side, we would essentially have to answer the same questions. We would have to look for the domain, vertical asymptotes, horizontal asymptotes, x-intercept, and removable holes. So remember that if we want to look for the domain, we're looking for all the x values that are on this function. So from the left hand side, we see that it's starting off, it keeps going on and on up until -infinity. So it's going from -infinity up until, let me use a different color so that you guys can see. And it's going up, it's continuing on and on and on up until this point here. This point is a vertical asymptote. And if you guys count on the x-axis, this is -3 because it's going by 2s. It's stopping, and then it's continuing on up here on top. On the x-axis, we're still looking at our x-axis. So this point up is continuing at -3, and then it keeps going. The function is still being defined up until this hole. On the x-axis, since that's what we care about, that hole is located at -2, and then it continues on from -2 up until, on the x-axis, what point is this on the x-axis? This is 7. This point here is 7. And then again, it's taking a break because of that vertical asymptote. And now it's continuing all the way down here at this point. It's continuing from 7, and it's going off until infinity. So it's going from 7 to infinity. So we have determined that we have two vertical asymptotes. The vertical asymptotes that we have are x equals -3 and x equals 7. Now we also want to determine our horizontal asymptotes. The horizontal asymptotes are the lines that it is a horizontal line that the function does not touch, and that is this line right here. This line is a line that has the form of y equals, and since it's passing through -3, this line is y equals -3. The x-intercepts are the points where the function touches the x-axis, and that is this point right here. That point is only one point, and since it's touching the x-axis at one point and then shooting right back up, that means that it has a multiplicity of 2. If we wanted to say to list the x-intercept, this x-intercept, it has an x-intercept at x equals 2, and if we also take a look, there is also a hole on this function right here, and that hole is at x equals -2. So if we wanted to determine the actual function of the graph, we would have to take all these points here and turn them into factors. We know that we can determine the vertical asymptotes from the denominator. So that means that these vertical asymptotes came from the denominator. Turning them into factors, x minus 3 as a factor is just x plus 3, and x equal to 7 as a factor is just x minus 7. Since we need to know the degrees of both the numerator and denominator for the horizontal asymptotes, we'll come back to that. But now let's look at the x-intercepts. For the x-intercepts, you know that we have to set the function equal to 0 in order to solve for the x-intercepts. And that means that the x-intercepts come from the numerator. So if we turn x equal to 2 into a factor, we get x minus 2. And by looking at the graph, at this point, we said that it has a multiplicity of 2. So that means that that is being squared. And by looking at the fact that it has a hole at x equals negative 2, then that means that the factor of x plus 2 was simplified in the numerator and denominator. So we have this function so far. Now we can take a look at the horizontal asymptote. And from the horizontal asymptote, we have to look at the degrees. So since we have an x being squared times another x, that is x to the third on the numerator, and an x times an x times an x, that is x to the third power. So both degrees in the numerator and denominator are 3. That means that the horizontal asymptote came from the coefficients. So that negative 3 should be right on top. And this is the function of the graph.